Oops. How should I go back? So it seems that without speaking anything, I'm finishing my presentation. So can you restart? Yes, thanks to Dr. Garbani and the organizers for having me on the stage. Otherwise, I would have been sitting all the day over there. So thanks for giving this opportunity. So I'm trying to make myself comfortable because there is a big difference sitting over there and coming to the stage and speaking here. So I'm trying to make myself a bit comfortable. And also I do the same, like when I'm traveling new places, like I'm going for a conference or somewhere, and then I try to make myself comfortable. So what new things I see there, right? And also when I reach to the hotel room, so first thing I do, okay, how does the lock work? Like, is that hope that I'm not leaving the door lock open. And also I do like this also quite happens with me sometimes at home. At the middle of the night, I wake up and I see that, did I lock my apartment's door? So, so I'm a bit curious, so sometimes I forget. So, but today I'm going to talk about different types of digital locks. So my research is on making digital locks. So, and we know, so thanks to the previous speaker, Rajiv, for introducing many of the concepts of what I'm going to talk about today. So, so today basically I'm going to talk about the lightweight cryptography and the recent NIST standardization competition. So NIST recently standardized a lightweight cipher. I'm going to talk about that. And then some of of course, it's in the standard, so industry is more comfortable to adopting them, but what are the real world challenges? I'm going to briefly talk about that as well. And also, when there is any primitive, so its applications is not specific to particular application. People may try to adapt them in different other applications. So I'll talk about a specific use case when we try to integrate any symmetric key encryption, more specifically the lightweight encryption with the homomorphic encryption technology, which has gained quite popularity in the recent days. So, so cryptography, I hope the audience, maybe many of you know what cryptography is and how do we use cryptography. So one is that, so we do browsing every day and we do secure browsing. And so one of the protocol that is used to secure the web is TLS. So TLS has a bunch of cryptographic primitives. So it has encryption algorithm, it has authentication algorithm, and many other primitives. So when we say security, so security has different meaning. In the cybersecurity world, people define security in different ways. But when in cryptography, we define security with the uncertainty of a probability 2 to the power negative 128. Or in terms of computation, it will take thousands of years to break something. So that's the kind of security we talk about. So it's a negligible probability. So now, so definitely if we want to achieve security, so these are the security properties like confidentiality, integrity, authentication, non-repudiation, etc. All these are the common security properties we need even we want to secure any application in the digital world. So any guess on what percentage of the web traffic is encrypted? Anyone? Anyone recently searched? We're curious. So different studies or surveys say that about 85%, more than 85% of the web traffic are encrypted. So if we look back the date a decade ago, that means in 2013, we'll see that even less than half of the web traffic were unencrypted. So, and that is happening due to the TLS. So now, so here are basically some like some of the surveys. I found it interesting. So if you look at this survey from the Poneman Institute, so and also this encryption consulting, they're talking about the trends in adopting encryption technology in industries. And you can see here, So in the first entry, so securing internet communication using TLS SSL. So it's about 83%. And if we come, and there are different other applications like databases, emails, etc. They are secured. And also, if we look at the Internet of Things, so they are a bit lower side, around 61, 63%. So encryption technologies are being used in different applications. So now, so these are some some basic things. And so welcome to our cyber titans. So these are the just to give some brief introduction on the cryptographic primitives. So there are basically two types of encryption. One is the symmetric encryption, public key encryption, and they differ by the type of the keys. For the symmetric key, there is only one key, and for the public key, there are two keys used in the encryption process. So encryption is nothing but a box with a lock. It's a physical world visualization. So we have a box and we have a lock. We just use the key to lock the box. That's it. So, and in the digital world, that is what we try to do. And there are also other primitives like we need like message authentication code. That means when we send any piece of information over some open insecure channel, we want to make sure that the data haven't been compromised. So we can achieve those using the message integrity code. And also if we want to detect the source of the data, then we can use a digital signature. So these are the kind of primitive we used. So there were like so far sometimes around 2009, then the RFID technology became very popular. So which basically created a new directions in cryptography. So before, NIST standardized the advanced encryption standard AES algorithm in 2001. And AES algorithm is not suitable many of this type of RFID sensor network, this type of resource constant applications, because these RFID tags, they are very cheap. So these days maybe we need the cost of an RFID tag is about the 10 cents, and we can afford 1 to 2 cents for the security. And there are different applications you can see, RFID, NFC, Zigbee, Internet, etc. So these are kind of some rough estimate about the budget, some we can spend on security. So now think of this situation. So we need to design encryption algorithm for the cost of 1 to 2 cents. So that's the kind of math we need. That's the kind of algorithm we need, so that they are suitable for the resource constant devices, and applications of those algorithms will also be in the resource extensive application, resource intensive devices as well. So this basically created a new direction, and lightweight cryptographic algorithms were designed. And even we are working in a constant environment. So only one primitive is not enough. For example, encryption is not enough. We need encryption, we need integrity protection, we need authentication, multiple other things. So this also created another challenge, that with minimal cost, can we achieve different types of security? So this and then NIST basically realized that we need a standardization, and when we have any algorithm, then we want to use it for the different purposes. One is that protecting communication. That means when data is in transit, and when data is in rest. So we have data and we want to store it at the database. So we want to keep it safe. So data storage security, and also data in use. That means we are performing some computation with the data. And these days there are popular technologies came like zero-knowledge, blockchain, which basically gave a popularity of the zero-knowledge proof technique, and homomorphic encryption for the encrypted computing. So if we look at the history a bit, we see that the NIST has the tradition of standardizing cryptographic primitives starting from 1970. So this was the first algorithm standardized by the NIST, and then over the years, many algorithms standardized SHA-1, SHA-2, SHA-3, and in the recent year, with the popularity of the Internet of Things, for example, cyber physical system, etc. So we need lightweight cryptographic algorithm, and NIST started the competition in 2019. And also, there is something interesting missing in this slide. So there is a parallel world, it's called the quantum world. So where NIST is also run a competition, and so many of you already know about the quantum competition. So now they are at the, they already decided the finalist. So lightweight cryptography is something needed from different applications. What you can see in the slide. So they are basically the RFID, Internet of Things, embedded system, etc. So now, when NIST announced the call for paper, they mentioned several criteria. They said that we need two types of algorithms. One is one algorithm that will be efficient only for the hardware. Another algorithm we need, which will be suitable for both hardware and software. And then how do we evaluate those algorithms? So there are different criteria. So we'll evaluate them with respect to the security. Just I want to mention one important point. So when you say that the lightweight algorithm, that does not mean we are compromising in security. We want to have the same level of security like a traditional cryptographic algorithm. For example, 128-bit security. So security, first, like algorithms should provide security. It should be efficient in hardware, software, because they will be implemented on a spectrum of different types of devices. And also other features, like for example, short messages. So the traditional algorithm like AES, SHA-256, this type of crypto primitives, they may not be suitable for the computationally efficient for the short messages. So this is one of the feature is required. And they basically come from the applications. So after publishing the call for paper from the all over the world, NIST received 56 algorithms, and they can be broadly categorized as authenticated encryption with associated data, AEAD, and hash. So the same algorithm provides both functionalities, and one type of algorithm that provides only authenticated encryption. So, and these algorithms are based on these constructions, permutation-based, block cipher, tweakable block cipher, stream cipher, and so on. So then, within 4 months, NIST eliminated 24 algorithms and kept 32 submissions as the second round candidate for the further evaluation. Then, and these algorithms are permutation-based algorithm, then block cipher algorithm. So these are some name of the algorithms. So I don't have enough time to go through them. But I just to get familiar with the names, or maybe in the future if you see them. So and then after more than 1.5 years of evaluation, they selected 10 finalists, and then again another almost less than 2 years of evaluation, they selected ASCON as the ASCON in their standard. So ASCON is a lightweight cryptographic algorithm. Right now it's in the NIST standard. So you can find the initial documentation from the NIST. So now let's quickly look at it, because this is not something what we are learned here, just how this is different from the other algorithms like AES and other things. So the ASCON algorithm uses the sponge mode, so which is the same structure as of the SHA-3, and they are using some common elements like that. You can see the digital circuit. So that's basically the S-box circuit. So that's a component of the encryption algorithm, and they added some. They use that S-box, that's the nonlinear component, and they also added a new layer, and which are actually computationally efficient. So they are efficient. They might be efficient for the lightweight devices as well as maybe, for example, for the traditional computers. And there are different variants of the proposed. So using the same structure with a little tweak, 3 different primitives can be constructed. Authenticated encryption algorithm that provide confidentiality integrity, the hash algorithm, which can be integrated with a digital signature, and also XOF, that's called the extended outputable function. That means it's like a hash, but with any arbitrary length output. So that's about the ASCON. And also my research is in this direction. So so then we proposed a ASCON-like algorithm where we aim to reduce the hardware cost further. So ASCON is a quite well-optimized algorithm, and we found that the sum of the components can be carefully chosen, which may lead to better hardware implementation. And of course, things don't. So there are, in the real world, there are always trade-offs. So we are sacrificing little bit in the software speed, but we have about 1,300 gate equivalent, 1,130 gate equivalent in saving. So, and this algorithm provides authenticated encryption and hash. By the way, one more thing, for the ASCON basically has a quantum variant, so which provides 80-bit of quantum security. And then, of course, so this new cipher. So now the cipher is standardized. So, like, of course, it has advantage on implementation with respect to AES. It's on both hardware and software. These are some performance results. I won't go much. So, ASCON provides a better flexibility in implementation. And these days, because you have seen in my earlier slide that Internet of Things, because there are many attacks on Internet of Things. Why is that? Because encryption is in the DNA of the digital world. Because if there is no security protection, we cannot survive. So then someday we'll see that these are some common cyber suit. If you have worked with TLSA, then you may have seen those. So now with the new algorithm, there may be some cyber suit you'll be seeing, like let's say TLS, ASCON or something. So there are many real world deployment changes come. So now you see there are many open implementations available, like OpenSSL, you may know, and also ULP, SSL, Embed. They are suitable for the resource constrained applications. So now Internet of Things is a quite diverse application. There are different type of devices. Some devices, for example, they implement the algorithms in hardware. Some they implement in software, in microcontroller. So now let's think of, there are two manufacturers. Like from the industry deployment point of view, industry has, like applications has wide variety of devices. They need to securely communicate with each other. So now in the market, AES was the only player. And now ASCON is in the market. So now how they are going to, suppose there are two devices, two manufacturers, they are implementing two different algorithms. Basically, they do not have any common algorithm to implement it. So, especially for the hardware-related devices or hardware implementation-related devices, that's quite challenging. And also, when there are multiple cipher suit, one of the key tasks in the TLS is the cipher negotiation, right? So, if there is no common cipher so that they both can use, then probably it's going to be a huge problem. So, there are a wide variety of attacks. The new cipher suit has to be evaluated with respect to new types of attacks. So now in our, so we can demonstrate that we can secure IoT applications. So in our lab environment, we see that just using the embed and on Raspberry Pi, we can install it and we can run the TLS. And here basically we see that the public key encryption, we know as usual always takes more time compared to the symmetric key encryption algorithms. So, some type of, so these primitives can be applied to the real world applications like Internet of Things. So far we talked about the two different things. So because let's try to recall, one of the goal is that the data analysis. So why do we collect data? So devices exchange data for performing a wide variety of tasks autonomously. Second goal of IoT is that collecting data from applications and analyze them. So analysis is important. So now if we deploy such a lightweight algorithm, we see that we can achieve secure data security in transit, data security at rest using the lightweight crypto algorithm. But we cannot perform the analytical computation on the data. So this is a big challenge. So we need, but there is a solution for that. So we can use the fully homomorphic encryption. So this primitive allows to perform computation over encrypted data. For example, you have two boxes locked with two numbers. Without actually opening them, we can perform the multiplication of those two numbers, 3 and 5. And similarly, we can perform the addition. But now the question is that the lightweight applications, they have the lightweight ciphers implemented. But lightweight ciphers cannot do any analytical computation. So without actually decrypting data in the cloud environment, how can we enable analytics? So there is a solution for this. So that means that our fundamental task is we need to convert the lightweight cipher into the fully homomorphic encryption cipher. So if we have the fully homomorphic encryption ciphertext, then we can perform the analytical computation. So now, like, so in the real world, suppose you have two boxes and you have a secret in one box, both boxes are locked. You need to transfer secret from the one box to another box. How do you do this? I'll leave you that as a puzzle. But in the digital world, there is a solution for this. So we can homomorphically decrypt the ciphertext and we can convert the lightweight ciphertext to a fully homomorphic encryption ciphertext. Then we can perform analytical computation. But this process is not simple. So in order to do this process, so basically what we try to do, we look at the circuit complexity of all the NIST lightweight algorithms, and we view them in form of a digital circuit, the literal circuit that is made of the Boolean gates like AND, XOR, NOT, etc. And so here is a stat, and we see that if we compare AES with the ASCON, then we see that ASCON circuit is better. And so how it would happen in the cloud, in the data conversion process, so it takes an encrypted data, it will produce an encrypted output. So for the ASCON type of mode, so we can convert the data in this way. I won't go too much in the detail. And we see that using the TFHE cipher, it takes about 13 minutes to convert a lightweight cipher text to the fully homomorphic encryption ciphertext. So, and for the AES, it takes about 21 minutes. So ASCON is performing better in this case as well. So here are some performance results for the other cases as well. So now, we have seen that concept, but how can we apply to the real world scenario? So here is an application for the critical infrastructure protection. Suppose smart meters, they implement the lightweight cryptographic algorithms and they outsource data to the cloud. And at the cloud environment, we can do the smart metering related analytics algorithm. And using our smartphone, we can control it. So we can set up the key for the fully homomorphic encryption, and we can send a query to the cloud using our phone that, okay, what was the, so when in the particular day, when I use the maximum energy at my home. So we can do that type of computation. What is my bill so far? So we can do analytical computation in that way. But with this, the best part of this type of solution is that we can have the full end-to-end full privacy. That means when the device is leaving data, throughout its transit, rest, and also in the use process, every time it's encrypted. Data is never leaked to the untrusted cloud environment. So here are some estimate results. So this solution is fantastic. So we built a prototype system for different queries like total energy consumption, daily, tariff-based billing, and so on. And so here are some timing results. So ASCON takes about 7 to 13 minutes in the homomorphic decryption phase, and also the private min, it takes 5 minutes, and also private analytics, it takes about 41 minutes. So we see the advantage. We see the privacy guarantee is assured, but we are suffering from the performance issue. So we need more research. And so far in the lightweight crypto domain, different considerations like hardware area, the code size, energy consumption, throughput, side channel resistance, those are the criteria. But this type of application says that when we design such cipher, we also need to take care of, we need to also consider their integrating application with the other crypto primitives. So this is what I wanted to share with you today, and thanks very much.